Hi friends, welcome to my channel JKD Gate Lectures. In the previous class, we discussed about characteristics of a switch. I hope you enjoyed this. Since this topic is very important, let us further continue our discussion and we'll discuss number of examples. We'll discuss in detail about each example. In most of the gate exams, you will find this type of questions. Mostly the questions, since gate test the conceptual knowledge, they consider the switch as an ideal switch. We consider the same thing here. Okay, let us go inside and let us see some of the important topics what we considered in the previous class. Now we discussed the properties of a switch, which is very important. If you understand this, you can answer many of the questions what we discussed in the previous class and this class. Now we consider two cases of operation of the switch: when the switch is on, when the switch is off. When the switch is on, switch voltage is equal to 0, load voltage is equal to battery voltage, switch current is equal to the load current. Now when the switch is in off condition, switch voltage is equal to battery voltage, so that the switch will be in off condition, load voltage will be 0 and switch current is 0. Now we'll go to the some of the important things here. In the previous class we discussed some of the switches and their characteristics. Here I want to discuss once again because this is very important. Now let us consider the first switch as the diode. Diode is a uncontrolled switch. When diode is forward biased, it will turn on. When the diode is turned on, the voltage across the diode is 0. Therefore, irrespective of the forward voltage you applied here, the voltage across the diode is 0 and the current passing through the diode is equal to the load current. Therefore, if you observe the characteristics of the diode, during the forward biased condition, for an ideal case, the voltage across the diode will be 0 and the current will be passing through the diode, then that current depends upon the load resistance. Let us take the other case, when the diode is reversed bias. When the diode is reversed bias, diode will be turned down. Irrespective of the voltage you are applying here, current will be 0. Since the current is 0, the characteristics lies on the negative x-axis. Therefore, this represents the voltage across the switch. Since the switch is in off condition, it is equal to the applied voltage and current will be 0. This is about the diode. Let us consider the next switch, nothing but the SCR. There is a small difference between a diode and a SCR. Diode is uncontrolled, there is no control, but SCR is a controlled switch. Here we have a gate signal, gate terminal. With gate signal, you can turn on the SCR. Okay, we can do turn on process only, not turn off process with the gate. Now, when I apply the forward voltage without the gate signal, okay, current will be 0. Therefore, since the current is 0, why the current is 0? Because SCR is in off condition. Since SCR is in off condition, current will be 0 and applied voltage will appear across the SCR. Therefore, you will get the operating characteristics on the positive x-axis like this. Here this represents the applied voltage. For example, if this is the applied voltage, you will get the operating point here. Now, if I apply the gate signal, now forward voltage is applied, now I am applying the gate signal. What happens? The switch will be turned on. Since the switch is turned on, the voltage across the switch is 0 and current will be passing. Therefore, you will get the operating characteristics on the positive y-axis like this. And this current depends upon the load like this. We will be getting the operating characteristics on the positive y-axis at different points. Okay, like this here. And since the switch is in on condition, since we considered an ideal switch, the voltage across the switch is 0. Now let us take the second case, a negative voltage. If you apply the negative voltage across the SCR irrespective of the gate signal, SCR will be turned off. Therefore, since the SCR is turned off, current passing through the SCR is 0. Therefore, you will be getting the operating characteristics on the negative x-axis like this. Here you are getting here because the current here is 0. This is because the switch is in off condition. Therefore, we can consider one thing here. With the gate, you can turn on the SCR, but you cannot turn off the SCR. That's why it is called as the semi-controlled switch. Now, one more thing here is I want to tell you here is gate is a very important thing here. With the gate you can do the turn on process, and it is a you can operate both bidirectional voltages here. You can give a positive voltage as well as the negative voltage. Now let us take the another combination of switch here where you have a BJT and a diode. BJT and diode are in series, and these characteristics are very similar to that of the SCR. Now when you apply the forward voltage without the base signal or without the controlled signal, the switch will be in off condition. Therefore, since I'm applying the forward voltage without the control signal, now the switch is in off condition. Switch here means the BJT. I'm talking about a BJT. BJT is in off condition. There is no current passing through the BJT. Therefore, your characteristics lies on the positive x-axis, and the voltage across the switch is equal to the applied voltage. Therefore, you are getting an point like this here. Now, and see the diode, it will accept current only in one direction. What happens if I give a negative voltage? If I give a negative voltage, this diode will block that voltage. Diode will be turned off. Since the diode is turned off, you will be getting zero current, and therefore whatever the voltage, the negative voltage you are applying across the switch will appear across the switch. Therefore, we will be getting the operating point on the negative x-axis. Forgot about the third case. If you apply the forward voltage and control signal is applied, means I am applying the base current, then what happens? This BJT will be turned on. Now since the BJT is turned on, the voltage across the BJT is 0. Since I am applying a forward voltage, diode will be turned on. The voltage across the diode is 0. So that the net voltage, which is nothing but the voltage across the BJT plus voltage across the diode, is 0. And current will be passing through the switch, the combination, and this current will be equal to the load current. Therefore, we will be getting the characteristics on the positive y-axis like this. Therefore, these two combinations work similar. One important point here I want to say here is you can apply unidirectional voltage to the BJT. You can't apply bidirectional voltages. You can apply unipolar voltages to BJT, MOSFET, and IGBT. Therefore, we consider this another switch nothing but BJT. You can take either MOSFET or BJT. You will get similar characteristics. Now let us apply the forward voltage to the IGBT without the control signal. Then it will block the voltage. Therefore, we will be getting 0 current, and characteristics lies on the positive x-axis. If you apply the control signal, the switch will be turned on and current will be passing, and therefore we will be getting the characteristics on the positive y-axis. Here one thing I want to say here is this diode can block only reverse voltage. SCR can block positive voltage as well as the reverse voltage, but it will allow only positive current. This combination can block positive voltage as well as the negative voltage, but accepts current in only one direction. This can block only positive voltage. Now let us enter one important question here which appeared in GATE. Figure shows a MOSFET with an integral body diode. It is employed as a power semiconducting diode in the on and off states through appropriate control. The on and off states of the switch are given on the VDS-IS plane. Here you can observe a MOSFET with a gate, drain source and anti-parallel diode connected to it. Now, which of these characteristics represent this MOSFET? Now, as I told MOSFET, we can apply unipolar voltage. Therefore, what happens? It will block the forward voltage. Okay, accepts current in positive direction. If you apply the reverse voltage, diode will turn on. Means it cannot block the reverse voltage. It accepts current either in positive direction as well as in the negative direction. Positive direction will be passing through the MOSFET. Negative current will be passing through the diode. Now, therefore, let us see the characteristics. Now, let us look into the first characteristics. As per this characteristics, it can block positive voltage as well as the negative voltage, which is wrong combination, which is a wrong choice. Therefore, it is a wrong choice. Here, if you see the C characteristics, it is showing that it can block positive voltage as well as the negative voltage. It is allowing positive current as well as the negative current, which is wrong. It can accept, it can block only positive voltage, it cannot block the negative voltage. If you see the D characteristics, it is showing it is blocking positive as well as negative, which is wrong. If you see this B characteristics, it is showing it is blocking only forward voltage. It is allowing forward current as well as the negative current. Negative current will be passing through the diode. When you apply the negative voltage, the diode will be turned on and it will be allowing that current. Therefore, this is the right choice. Therefore, B is the right answer. Now, let us see another question. In the circuit of adjacent figure, the diode connects the AC source to a pure inductance. Now, the diode conducts for. Now, we'll discuss one more question and solve both the questions with single answer. The circuit shown in the ideal shows an ideal diode connected to a pure inductor and is connected to a purely sinusoidal 50 Hz voltage source. Under ideal condition, the current waveform through the inductor will look like. Here I have a voltage source, a diode and an inductor which is similar to the previous figure. Now here is asking about the waveforms. Which current waveform is representing the actual current waveform? In the first waveform, for 20 milliseconds there are 4 positive pulses. In the second answer, for 20 milliseconds there are 2 positive pulses. In the C, for 20 milliseconds 1 positive pulse. For D, it is showing 1 positive pulse and the second half is 0 current. Let us see which is the right answer. I will tell through mathematical as well as through conceptual. Now, if you apply the forward voltage, diode will turn on. When the diode is turned on, source voltage is equal to load voltage, which is equal to the L into di by dt. If you derive the current expression, we'll get a current expression like this. At omega t equal to 0, current is 0. If you integrate it, you will get the current waveform like this. Now in the next slide, what I will do is, I will plot this current waveform and I will analyze this circuit. Now here, this represents the supply voltage. This represents the output voltage. How I got the output voltage like this? Let us look into this. Now after plotting that expression what I get in the previous slide, I got a waveform like this. Means for one complete one complete cycle of supply, I am getting one positive pulse. How I got like this? Because this is based upon the expression. Let us go with the conceptual answer. We know that voltage across the inductor, which is nothing but the output voltage, is equal to L into di by dt. Now as per this, di represents change in current, dt represents change in time. If current is if the current is rising, I will get a positive voltage. Or in other word, if you reciprocal it, if the voltage is positive, it means that current is rising. If the voltage is 0, it means that the derivative should be 0, means current should be maximum. If the voltage is negative, it means that current is falling. Once again I will repeat, if current is rising or if the current is increasing with respect to time, voltage across the inductor is positive. If the current reaches the peak value, voltage across the inductor will be 0. During this period, inductor will be storing that energy. In the second half cycle, inductor will be delivering that energy back to the source, because we know that inductor is energy storage element. It can store the energy and deliver that energy. Even the voltage enters negative, even the supply voltage enters negative, but still energy is there in the inductor. Therefore, the switch cannot turn off. If the switch turns off, the entire energy appears as a spark across the switch. Therefore, what happens, even though the supply voltage enters negative, still energy is there in the inductor. The current cannot go to negative, or the SCR cannot stop conducting here. Therefore, you will get one positive pulse for one cycle. Since the frequency is 50 Hz, 1 by 50 Hz is equal to 20 milliseconds. Therefore, for 20 milliseconds, you can get one positive pulse. And if it is the first question, for how many degrees for what duration for which this diode will turn on? It is for entire cycle, means 360 degrees is the answer. Therefore, if you go to that, therefore if you see this, right, now the diode connects for 360 degrees is the right answer. Now circuit 3 here, answer here is 1 positive pulse for 20 milliseconds. Therefore, C is the answer. Now another question. A typical switching waveforms for a power transistor are shown in figure below. Switching losses during turn on is here. If you see that current is rising, means initially it is off and it is settled, means it is turn on process. Here if you observe the voltage also, initially voltage is high, later voltage goes to 0, means there is a turn on process here. During this process, turn on process, what is the energy loss? What is the energy switching losses? For this case, let us see the answers. VCC into ICS by 2 into turn on. The second one is by 4, by 6, by 8. Let us see the derivation. Now here current is rising, here voltage is falling. Therefore, if you write the expression, this is a equation of S. It is in the form of a straight line passing through origin. Therefore, it is in the form of y equal to mx. Therefore, if you write the expression for IC, y equal to mx. Mx means what? Slope. Means when time changes from 0 to t on, current changes from 0 to ICS. Therefore, slope is ICS by t on. Similarly, if you write this expression of this voltage, it is an equation with a negative slope. Equation of a straight line with a negative slope. Now, therefore, when time is 0, the voltage is VCC. Therefore, you can write this VCE as slope, negative slope. What is the slope again? There is a difference between this. Here the current is rising, here voltage is falling. The slope will be same, approximately VCC by T on. Therefore, we'll find the power equal to voltage into time. Now, if you derive this, if you integrate this, you will get the energy. Let us integrate to get the energy loss. We need to integrate from 0 to t on so that I can get the switching energy loss. Almost the questions are same here. Sorry, t on square you will get. Positive term is same. One is t, the other one is t square. Therefore, if you integrate it, you will get one in terms of t square by 2, the other one is t cube by 3. If you substitute that 0 to t on values, finally you will get the answer as Here T1 will get in the numerator, therefore the answer, if you see this, answer for this is C. Now see the question. A MOSFET rated for 15 amperes carrying a periodic current as shown in figure. This is the figure. The on-state resistance of the MOSFET is 0.5 megawatt, 0.5 watt. The average on-state losses in the MOSFET is, now it is showing that in order to calculate this, if you know the current and since you know the resistance, if you find the power loss for a period of 2 pi, you will get the answer. Okay, you'll try this, all of you. We'll start our next lecture with this solution. Now the next lecture is SCR as a switch 1. There are two we have discussed. We'll discuss this SCR as a switch in the next class. If you like my lecture, please subscribe, like and share. Hi friends, welcome to my channel JKD Gate Lectures. In the previous classes, we discussed about characteristics of a switch. We discussed few example problems that appeared in Gate. I take this opportunity to continue this power electronics and deliver to you wonderful people. Now let us continue our lecture. Now this lecture focuses about SCR as a switch. We'll discuss multiple lectures on this. Now let us first start our lecture with an SCR. SCR means silicon controlled rectifier. It is a semi-controlled switch. We'll discuss SCR like a switch. Therefore, we'll discuss about the SCR. SCR is a semi-controlled switch. Now if you see the construction, there are four regions: P, N, P, N. Now this I will name it as P1, this as N1, P2, N2. Now because of four regions, three junctions are formed. Junction J1 is in between P1 and N1, J2 is in between N1 and P2, J3 is between P2 and N2. Now if you see that doping levels, to understand the switch, let us look into the doping levels and let us understand it. On this P1 is N1 is lightly doped, N2 is heavily doped. This occupies more space, and while this occupies very less space, these two are moderately doped and they occupy moderate space. If you see that junction J1, it is formed between two lightly doped, or we consider it one is a lightly doped region. Therefore, the junction J1 is formed between two lightly doped regions, and this J1 requires very high voltage to break down, while J3 is completely opposite to it. J3 is formed between two heavily doped regions. Therefore, very less voltage is required to break this region. Now, similar here, the same thing here, J2. J2 is also formed between two lightly doped and requires very high voltage. Now, there are three operating regions of the SCR. One is forward blocking, the other one is reverse blocking, the third one is forward conduction. Now there are three regions. This comes under region 1, this comes under region 2, this comes under region 3. Now in the forward blocking region, means here what I will do is I will apply a forward voltage to the SCR. When I apply the forward voltage, P1 which is connected to the positive and N1 is connected to the negative. Therefore, if you observe this, J1 is forward bias, J3 is forward bias. J2 is reversed bias. Therefore, this J2 is blocking the entire voltage. It is blocking the current passing from anode to cathode. It is block. This is the switch here. I can say that this is like acts like a wall and block the current. Now, in this region without the gate pulse, what happens is if you apply the voltage, the current is very low in terms of microamperes. This current we call it as a leakage current. Ideally, this current is zero. Practically, this current is in terms of microamperes of current. Since the operating currents are in the range of kiloamperes and 100 amperes or 20 amperes, I can consider microamperes of current as zero current. Means this leakage current is almost equal to zero. Now here, if I increase this voltage, this leakage current slightly increases. Still, it is in the off state. When the applied voltage is beyond a voltage called as the forward breakover voltage (SCR) goes to conduction without control. Now, this method of turning on this method of turning on is not a reliable method because this method may damage the SCR. SCR may burn within one time. Therefore, this is not a suitable way to turn on the SCR. Now, we require a control. Whenever a switch is there, we require a control. Whenever we want, we can turn on the switch. That control is nothing but the gate. Now, what I will do is, with forward biased condition, I will apply a positive voltage across the gate. Here, I will apply a positive voltage. Positive voltage is applied across the gate and negative voltage is applied across the cathode. Now, under this condition, what happens here is this this region is flooded with holes, and these holes will break the J2 junction, and current will pass from anode to cathode. Now, to control 100 amperes of current or 1 kiloampere of current, some milliamperes or 1 ampere of gate current is sufficient. That's why we call it as a control signal. Now, this is considered to be comes under this region. This is called as the forward conduction region. Here it is represented with blue color here. This is called a forward conduction region, where SCR acts like a on switch. In the forward blocking, SCR acts like a off switch. Here SCR acts like on switch. Here off. Here it is on. Now, here there are two important currents we need to discuss that are called as the latching current and the holding current. Latching current is the minimum anode current required to turn on the SCR even after the gate pulse is removed. It means that if you apply the gate pulse, SCR will turn on. But if still the current is below the latching current, if I remove the gate pulse or gate signal, SCR goes to off state. Means I can say that SCR is not completely turned on unless until the current reaches the latching current, and once the current reaches the latching current, gate loses its control. That's why the latching current is defined as the minimum anode current required to turn on the SCR even after the gate pulse is removed or gate pulse is stopped. If you don't understand this, you don't understand the latching current, and you will find number of questions in gate based upon this definition. If you understand this latching current definition, you can solve those numerical examples. Those numerical examples we'll discuss in the next lecture. The other current is the holding current. Now SCR is turned on. SCR is turned on means gate has no control. Gate is losing its control. Once SCR is turned on, I need to bring it to off state. To bring it to off state, if I make the current below the holding current, the anode current falls below the holding current. The instant anode current falls below the holding current, SCR goes to off state. That's why this holding current is defined as it is anode current below which SCR goes to off state. Now, Let us apply the reverse voltage. Reverse voltage means I will apply a negative voltage to the anode and positive voltage to the cathode. Now if you understand, J1 is forward bias, J1 is reverse bias, J3 is reverse bias. J1 is reversed bias because P-type material is connected to the negative and N is connected to positive, therefore it is reversed bias. This is also reversed bias, but J2 is forward bias. Okay, this J2 is now not the blocking the current. These two junctions are blocking the current. Out of these two junctions, this J3, which is the junction point between two heavily doped regions, cannot block much current, much voltage. Means this actual J3 is not blocking the current under reverse voltage condition. The J1 is blocking the current. If SCR is reversed bias, the actual thing that is happening here is J1 is blocking the current and it is not allowing the current from anode to cathode. In this condition, SCR acts like an open switch. Okay. Now here also, here some current is passing here. That current is called reverse leakage current, and it is almost equal to 0. When the voltage is uh, beyond VBR, reverse breakdown voltage, SCR goes to unstate and higher current will pass and may damage the SCR. Hot spots will be found and SCR is damaged. Therefore, if you see, you need to see that your operating voltage should be less than the reverse operating voltage should be less than the VBR. In this VB0 and VBR is higher than VB0. Now let us take one question which appeared in GATE exam. Here there is no relation between the question and the SCR characteristics. Here SCR is the switch, that's all. Now thyristor T in the figure below is initially off and is triggered with pulse width of 10 microseconds. It is given that L equal to 100 by pi microhenry and C equal to 100 by pi microfarad. Assuming that latching current and holding current of the thyristor are both 0, the initial charge on the capacitor is 0, T conducts for. Yes. If I turn on the switch will turn on, but the load is a LC load. This load is an LC load. Now both are energy storage elements. Let's see what happens. Now when the SCR is turned on, if you apply the KVL, the voltage across the inductor plus voltage across the capacitor is equal to the nothing but the voltage across the load is equal to supply voltage. Voltage across the inductor is L into dA by dt. Voltage across the capacitor is 1 by C integral I dt. The sum of these two voltages is equal to Vs. Now applying the Laplace transform, we got like this. Now initially, let us assume that initial current is 0, initial capacitor voltage is 0, capacitor charge is 0. Now considering that initial conditions, applying the Laplace transform and applying the inverse Laplace transform, I got a current expression. Now this is the current expression, I got it. Now this current expression I of t equal to Vs supply voltage into root over C by L sin omega naught into T. This is called as resonant frequency. Since the circuit is a resonant circuit, we will get a resonant frequency which is value equal to 1 by root LC. Okay. Now this is a current waveform is a sine wave. Now the sine half of the cycle will be completed when omega naught t equal to pi. The time at which the current becomes 0 is omega naught into t should be equal to pi 180 degrees pi. From this t naught equal to pi by omega naught and omega naught equal to 1 by LC. Now here let us plot the waveforms. Current is a sine wave. Actually without this SCR it will go to a negative of cycle also. Since SCR is there, Since it accepts current only in one direction, current will be 0 at this point and SCR will be turned off at this point. Now this is the duration for which SCR is turned on. We need to calculate this duration. Now if you see that now this is the current passing through the inductor, nothing but the current passing through the capacitor. As I told in the previous class, current is rising. The current is rising, voltage across the inductor is positive. It means that inductor is storing the energy. Now current is falling during this period. Current is falling here, it means that voltage across the inductor is negative. Voltage into current is negative. It means that inductor is delivering that energy to this. Inductor is delivering the energy. Now during this case, capacitor is storing that energy. Now from this region, inductor is delivering that energy and capacitor is taking that energy. Without inductor, capacitor will charge up to Vs. With inductor, capacitor charges up to 2 Vs. That is a very important thing here. Without inductor, capacitor can charge. If it is a RC circuit, capacitor will charge up to Vs only. Since it is a LC circuit, inductor is delivering the energy after half of the conduction. What happens? Capacitor voltage will charge up to 2 Vs. Now if you see that, as I told earlier, during this, when inductor is rising, when current is rising, voltage is positive. When current is maximum, current voltage is 0, and here it becomes negative. Since voltage is becoming negative, Vc is becoming 2 Vs. Now what happens here is, at this point of time, when current is 0, this capacitor SCR voltage becomes negative, means a reverse voltage is applied across the SCR. SCR will be turned off. Now the conduction time of the SCR is equal to, as I said, omega naught T equal to when angle is equal to pi, okay, then current will be 0. Therefore from this T equal to pi by omega naught. Pi by omega naught, if you substitute that, you will get pi into LC. Now this will be equal to what happens here, root over pi square will becomes pi, 1 by pi, and pi will get cancelled, 100 and 100 square. Now it is on top minus omega, therefore answer is 100 microseconds. Now let us take the second question, which, as I discussed earlier, thyristor T shown in the figure, the first figure. Here he is talking about this figure, the basic figure. Shows a thyristor with standard terminations, anode, cathode, and gate, and the different junctions J1, J2, J3. When the thyristor is turned on and conducting, see that it is talking about during conduction mode. When conduction mode, what is blocking the current? Nothing is blocking the current. All regions are forward biased. That's why current is passing from anode to cathode. If any one junction is blocking the voltage, current cannot pass. Therefore, I can say that all the junctions are forward biased. Other answers are J1 and J2 are forward, J3 is reverse, which is wrong. Similarly, here is saying here J3 is reversed by J2, J2 and J3, which are all wrong. When SCR is in conduction, all are forward biased. That's why current is passing from anode to cathode. Therefore, the answer here is D, which is appeared in one of the previous gate exams. Now, the typical ratio of latching current to holding current in 20 amps thyristor is. Now, here, if you see that, now this is the latching current. The first one is the latching current. The below one is the holding current. So it is wrongly written here. This is latching. This is holding. This is latching current. This is holding current. Now, as you observe this, latching current is somewhat higher than the holding current. But the answer is you want the ratio, latching by holding. Now from that graph you can observe that latching current is greater than the. Now since latching current is greater than, there are two possible choices. Both cannot be equal. Latching current cannot be greater. Now both, if you see that options 5 and 2, latching current cannot be very much higher. Latching current and holding current are somewhat closely related. Therefore, B is the answer. Our next video is SCR as a switch. We'll continue our discussion further. We'll discuss many numerical examples. Now, if you like my lecture, please subscribe to this channel, like and share. Thank you.